Welcome to another session of information retrieval. Today we will focus on query understanding. So our agenda today is to understand the query types, um, uh, how different users formulate their queries and why would they do it so would be one of our agenda items. And then we move on to the methods of query understanding. And here we particularly focus on token level query processing ideas such as query segmentation, spelling correction, and phonetic correction. I hope you remember this picture, which summarizes the way we have organized this course. We start with the whole process here starts with crawling the contents to be indexed, and we worry about index compression due to the sheer size of the content that we want to search. We are interested in relevance and ranking of our retrieval system, and also to evaluate how well our retrieval system did. In this whole process, there's another important block numbered as 4 in this picture, which is query understanding, which deals with everything about the query. So when there's a user who wants to interact with our system, how does he actually query? What is he actually looking for? How does he convert his information need into a query, and what all could go wrong here? What challenges should we expect in dealing with these kind of queries so that we build a better retrieval system? That is the focus of today. Some queries are just too hard to understand. Take this for an example. Um, so I just hit IR on the query bar on Google, and I was hoping that I would get information retrieval. But it turns out that Indian Railways is much more popular than information retrieval. So Google brings up Indian Railways website at the top. So it looks like there are a lot of factors that depend on how a search engine reacts to a query, and this causes some kind of synergetic relationship between the user and the retrieval system. So once the user understands how a retrieval system behaves, he changes his way of querying. And on the other hand, the retrieval system is always trying to improve its search performance, thereby trying to understand how a user wants to query, or what the querying style of a user is. And many of these queries also seem to depend a lot on the context. So if I have been querying a lot on IR over time, then probably these search engines can understand what I'm querying about. All right, so that's why query understanding is quite hard. So now look, let's visit the different query types that we often encounter. The first query type is what we call as navigational query. Well, who wants to type facebook.com on the browser anymore? So we are just happy typing FB and press enter. Google will show you Facebook, and then we just hit on the link, the first link, and go to Facebook, right? So this may not just be applicable to Facebook. You could think of many other sites that you might have visited this way. So these kind of queries where the intent is to navigate to another page but through the search engine are called navigational queries. And then we have informational queries. Let's say I just want to know more about an entity. I would just type his name and hope to see a information box with all the information that I would like to see there. And then there is this third type of query called the transactional query. Usually these are the first step towards a task that I want to accomplish. So let's say I want to book a ticket from Chennai to Delhi through air. I would probably query like this: Chennai to Delhi air ticket, and then I would hope to see some routes and some ticket offers, some major air ticketing agents showing um, uh, their offers, or their ticket availability information, and so on. And from there I start navigating to their site and complete my transaction. So there are these kind of popular query types. There is also a query type which is based on how long the queries are. So we typically call those queries that are 5 words and less as short queries. So usually, typically the queries are short phrases. For example, data science degree, India, Stanford, semester start date, and so on. However, long queries are also not uncommon. So here is a query which I took from a paper published in 2010 by Balasubramanian, Kumaran, and Carvalho. Easter egg hunts in Northeast, Columbus parks, and recreation centers. So these queries are not that uncommon. So queries of length 5 words or more have increased at a year on year rate of 10%, claim these authors, while single word queries have dropped by 3% as per their study. So that's quite interesting. So this goes to say that we need to focus both on short queries as well as long queries when we are building a retrieval system. There are also head and tail queries. So head queries are those queries which appear very frequently by volume. The number of users or the number of times a particular user queries it. So if you count the frequency, then the head queries are the ones with the large volume. So usually head queries get a lot of attention, and all search engines want to do well with head queries. In that process, they overlook the importance of tail queries. Uh, these so-called rare queries might be seasonal in nature. So let's say there is a World Cup competition coming up, let's say chess or cricket or Olympics or something like that. All of a sudden, there is a lot of queries related to it, and these queries are very important at that point of time. And these are the queries which kind of take away a big market share from one search engine to other, when the search engine fails to honor or perform well for these kind of queries. So the tail queries are also important, even though if you take a long average over time, they might not contribute to the volume a lot. Um, Here is an example where a query such as pizza would probably count as a high volume query. Many people are probably searching for it, but as you keep adding phrases to it, for example, pizza delivery in Boston, as the length of the query increases, the volume of the query drops, which is understandable. The probability that pizza would be a query should be much larger compared to the probability that somebody would query for pizza delivery, right? So the more and more phrases we add, the volume usually drops, and that explains why long queries typically form tail queries and short queries end up being head queries. But then there are exceptions to this idea. There are also queries which are of the question and answer types. Consider this. Who is the president of America? And Bing instantly told me it's Donald Trump. Uh, this is at least 2020 August at the time when I'm recording this video. So it seems the intent of this query is pretty clear, and the answer need not be a collection of documents. It just can be information. And the same is so you can come up with many examples for this. Well, the interesting part here is, how did Bing do this, or how did Google do this? How did Google know that Mecca is a holy city? um, so it seems with all the data that these search engines have, it's it's possible to extract information from these data, from these documents, and construct structures such that we could do question and answers. One common way of doing that is through knowledge graphs, which we will keep for discussion at a later stage of this course if time permits. But for now, please allow me to move on with the basic overview that even these type of queries exist. So the point that I'm trying to make here is that if your retrieval system should perform well, and should be liked by a wide variety of users, you should perform well on all these different types of queries. Okay, so that said, let's now focus our attention on the different methods for query understanding. The query understanding methods range from the simple token level query and query processing methods to the more complicated query reduction, expansion, and rewriting methods. So in this talk, we'll focus on the token level query processing methods, where we take the query and take each token one at a time and ask, can we do something about this token to better understand this query? Usually, the problem that we encounter in a query at a token level are spelling errors, and people forgot to put the spaces, so the phrases are not well segmented. The words are joined together, they appear together, and we have to figure out that these are actually two words and not a single word, and so on. And there is also phonetic correction, which we would like to focus sometime after discussing these things. At the more advanced level, we also have query reduction. As we see that the head queries, which appear many times in our query log, um, are short in nature. Most search engines are tuned for handling short queries. So the question now is, if I get a long query, can I do something about it and reduce its length so that I perform better on that query? Maybe the query is using too many stop words. I could probably remove them. That's one simple idea. And there are much more complicated ideas and strategies here for query reduction. On another note, I might sometimes want to expand the query. So consider the case where you use a word which is rare, but then its synonym is much more common. Uh, or in some cultures, some terms are used interchangeably. For example, in India, it's not so uncommon to treat hotels and restaurants the same. So if someone is saying he visited the hotel, he probably visited it to have food and not to stay, in the context as in the context of a restaurant. So by uh, uh, adding another word, restaurant or hotel, probably we now get better recall over that query than if we had just used the original query. So expanding the query with synonyms is just one example for expansion. And there are many other cases where I would like to add some location information or context information, user information, and so on, so that the expanded query is able to locate the document much better. Finally, there is this query rewriting set of techniques, which are different from reduction and expansion. So we are not only looking at adding or removing terms to the query, but we might completely rewrite the query. And we believe that such a rewrite of a query or a new query obtained from the existing query is of use. One example is the IR example that we took. Probably rewriting IR as information retrieval would have got me the results that I want, instead of adding anything to IR or removing anything from IR per se. That's it. Let's start now focusing on token level query processing ideas. So let's first start with query segmentation. Let's say I have a long phrase like State Bank of India or Amazon Prime Video. Um, Many users might, in the hurry of typing them out, might miss some spaces. So let's say I have a word and I want to know if a segment, if it is possible to segment that word into words, segment that one single word into multiple words such that they make more sense. How would you do this algorithmically? Can you give an algorithm to check if the input can be split to arrive at dictionary terms? What do you think? This is a good time to pause the video and think, if you were to do this, how would you do this? I repeat, the problem is you have a dictionary of known terms and here is a compound word given to you without spaces, and you have to check the dictionary and split this word such that every word uh, after splitting is a word in the dictionary. How would you do this? Let's take a look. This can be achieved easily through a recursive algorithm. The idea is to start from the first character and keep and keep moving our pointer, and try to put a space at every location possible and check if the uh, the term read so far is in the dictionary. So of course, right after reading the first character, if I put a space here, um, if I put a space here, then S is not in the dictionary. Let me just switch the presenter view. All right, so this is not in the dictionary. So I keep moving till I find a word which is in the dictionary. So let's say state. So after reading the word state, I do find state in my dictionary. So I consider that this is one candidate to be taken. But if I just take this, I'm being greedy, and it's possible that the rest of the terms do not find themselves in the dictionary, or maybe there is no way to split them in such a way that uh, they exist in the dictionary. It's just possible. Um, so in that case, what do I do? So for example, if I just keep moving here, AT add, let's say, or ATE8 could be in the dictionary, but if I split ATE8, then ST doesn't exist in the dictionary, right? So what do I do? So one way to address this problem is to take the remaining part of the word and apply the same algorithm to see if I can get to a word which is in my dictionary, and if that word is taken out, I see if the rest of the term can be split such that they are in the dictionary. And I keep recursively doing this, and at some point of time, if we see that there are some characters which we cannot map to the dictionary items, then we backtrack and we drop the idea of putting a space at that place, and then we keep reverting. So this is an example of a backtracking algorithm. So here the challenge is, after I put a space at state, I want to take the rest of this and try. So if I keep doing this recursively, I find that State Bank of India is a good split, and all the words appear in the dictionary. How would you do this? So here is a uh, example in Python. It's a simple idea of recursion, where we take the dictionary and we take the string, and we keep incrementing the pointer and we keep track of the pointer. So basically, from wherever we are, where the pointer is pointing to, till the end of the string, we take that substring and try if we can split that again. So this keeps happening recursively till I am done. At some point of time, if it doesn't work, we just backtrack, and we continue for searching for different combinations from there. So a recursive algorithm falls in place very nicely for that idea. So here I assume my dictionary is very small with just these words, and here is a query term, and I could just do this. You could try this with some other dictionary terms and play around and try to understand this algorithm yourself in more detail. Another form of problems or challenges with the queries is the spelling errors. Uh, Mercedes Benz or Mercedes Benz or Mercedes Benz. I don't know which one is the right query. Let's say, and let's say if you look at our query log, we find all these things, and we should identify that all these actually are referring to Mercedes Benz, and I want the user to see the results as though they would have queried for Mercedes Benz. So this is a case of spelling correction. Now, how do we know, how do we detect, and how do we correct spelling mistakes? Spelling mistakes are a usual thing. They happen for many reasons. Someone might be just typing quickly. or just that some keys are so adjacent in the keyboard, and maybe the pressure on the keys are so high that the keyboard is acting faulty, or there could be some inconsistent rules in the language, like in this case, so I comes before E or E comes before I. It's very hard to remember unless you have some experience with these words. Yeah, there could also be problems with some ambiguous word breaking rules in the language, like silverlight or silver space light. How would you write silverlight? And then if you have not seen some words, you just don't know how many n's to put, for instance, in connect. So these are usually some causes of misspellings, and due to these reasons, it's very common to see misspellings in queries, and it's essential to fix the queries. They say about 10 to 20% of the queries carry misspelled words, and English is not 100% phonetic. That is also another problem. For example, kernel is not written the way it is spelled. Read and read and dead are pronounced differently. Um, how many of these phrases do you think contain spelling errors? Just pause the video here and take a guess. Well, all of them have spelling errors. The cigarette, the party, the library, unforgettable, and successful. All of them have spelling errors. It's very hard for even seasoned graduates to spot all the spelling errors. So that's just the language thing, I believe. Especially if you are not a native speaker of English. Okay, here is another interesting example from Google's archives. So here are all the possible misspellings of Britney Spears that we see in the query log. It's fun to work with query logs. I'm happy I had an opportunity to do that. So when you look at the query log, so you can even get the frequency of how many times these terms appeared. For example, Britney Spears was spelled this way for the most amount of time. So this gives a clue that probably this is the best spelling, or this is the correct spelling for Britney Spears. Whereas some spellings are too rare, so these are all probably wrong spellings. These are highly probably wrong spellings, and there are some which are frequently misspelled. So they are close, but probably wrong. So now that I have this kind of a log, it helps me, makes my life much easier to detect spelling mistakes and even to correct them. So the question is, how close are we to a known term in the query log? There are two major approaches. One is to find the nearest dictionary term for any query term, and when we have multiple choices for the nearest dictionary term, then we go for the most commonly used term by frequency of the query. And there are two major kinds of spelling correction. We could do isolated term correction, which means we take one word at a time and ask, is this the right, is this rightly spelled, or should we correct it? And we go ahead and correct it. And there is also context sensitive correction. So here is an example for context sensitive correction, where form by itself is a dictionary word which is perfectly all right, not misspelled. But the moment you put form in this phrase, you know that there is something wrong, right? Flew from New York sounds much better than flew from New York. This became obvious only when we saw the context. So if you have a context and if you use it, you do a context sensitive correction. So now let's take a look at the one of the isolated term correction strategies, which is the edit distance based measures. So what is an edit distance? Given two strings S1 and S2, the minimum number of operations to convert one to the other is called the edit distance between S1 and S2. Operations are typically at character level. Let's say we consider only three operations: insert, delete, and replace. So usually you could add more to this, like transposition and so on. For now, let's think of these three as the legal operations that you could do. Then the edit distance from doff to dog is just 1, because all you have to do is remove f and put a g over here. Okay. What about cat to act? Well, so in this case, T remains where it is, but C and A needs to be swapped. So what could we do? So we could delete C and then insert C after A. So that's 2 operations. So we have cat to act as 2. In this example of cat to dog, I need to change every literal. So I need to replace C with D, A with O, and D with G. So I do 3 replace operations, thereby ending with a edit distance of 3. So what do you think is the edit distance between Sunday and Saturday? It's a good time to pause once again. Take out your pen and paper and work it out yourself. Okay, for the live audience, let's move on and explore an algorithm to do this. Before I jump into a systematic way of solving this, let's discuss how we could do this at a higher level. So if you have Saturday and we want to convert it to Sunday, we know that both of them have S followed by some characters and then day. So S and day stay where they are. The problem is then converting ATUR to UN. So what is the edit distance between this and this? So that's what we are asking. Well, if you want to convert ATUR to UN, so let me see if I can get my pen working. Awesome. So if I have to convert ATUR to UN, I could drop A, T and replace R to N, right? So drop these two and then replace R to N. So 2 deletes and 1 replace, that should give me edit distance of 3. This can get really confusing with some long strings. So it's good if we have a systematic way to do this. So can you think of an algorithm to do the same thing? What would you do if you were to devise an algorithm? A well-known efficient way to do this comes from the dynamic programming world, and this is called the Levenshtein algorithm. So let's see what the idea is. So if you already understand what dynamic programming is, then you can probably skip the next 5 minutes or so, because it's going to be obviously easy. But if you have never seen a dynamic programming concept before, then this can be a really difficult thing to understand. So let's say I write down one of the words Saturday on one axis like this, and let's have Sunday on this axis. All right, so we are constructing a table with these characters there, and of course read this as 5. It's nothing here. um, the question is, if I have nothing, and what does it take, or how many operations do you need to do to arrive at this? So from 5 to 5 I don't need to do anything. That's why I have 0 here. Now if I have nothing and I want to arrive at S, then of course I have to do one insert. So that's why the number of operations is 1. So remember, we are talking about only 3 operations: the insert, the delete, and replace. So these are the only 3 operations you are allowed to do. Okay, so now if I have nothing and read this as not just A but SA. Okay, so this is 5, this is S, this is SA, and this is SAT, this is SATU, and so on, right? So if you have nothing and you want to arrive at SA, what would you do? Well, the answer is simple. We just add one more character, so that's one more insert. So Let's just add 1 to this so that we get 2. So we need 2 inserts to get to SA from nothing. And what about SAT? Well, it's 3. What about SATU? That's 4. So rest of the thing is trivial. So we just write down 0 to 8 here. So if you give me nothing, it would take me 8 inserts to get Saturday. Okay, so this part is easy. And the same logic applies to the first column as well. So if you start from nothing, or let's go even this way, if you have nothing and you want to reach nothing, 0 operations are required. But if you have yes and you want to reach nothing, then you need to do 1 delete operation, right? So this is that 1 delete operation. So if you have SU, so this must be read as SU, and similarly we read this as SUN, SUND, SUNDA, and so on. And finally Sunday. Okay. So now if you want to convert SU to nothing, then you need 2 delete operations. So that's why we put a 2. So we can go on and fill this column. So we have 0 to 6. All right, so this is easy too. Now let's start worrying about this cell. So what's happening here? So I have an S already and I want to change it to S. Well, you don't have to do anything because you already have a S and your target is also an S. So that's 0. Yeah, 0. Okay, and if you have a S and then you want to get a, then of course you need to do 1 insert operation. So that's why that's a 1. And to T, it's SAT now. From S to SAT, you need 2 insert operations and so on. So it's easy to fill the rest of the cells here. Let's do one more row. So let's say I have SU. Now, from SU, if I want to reach nothing, I need to do 2 deletions. That was easy. We have already done that. Now let's take a look at this cell. So what are we trying to achieve here? So from SU, I want to reach S. Okay. So in order to reach S from SU, what could you do? Right? So you could take SU and just delete a U to get S. Okay, so that's one way to reach S. Another way to reach uh, uh, so this is by deleting. So you could, can you do any other inserts, can you do any other replacements? So you could think what other ways could you reach here. Well, it seems there's no other way to reach from SU to S. The easiest way is just remove a U. Yeah. Any other way is more expensive. Like for instance, I replace this S with U and let's say I delete this U. Then I have 2 operations, which doesn't sound correct, right? So just 1 operation is sufficient. Okay. And then what happens for SU with SA? So my target is SA, but my source is SU. So since S is common, all I have to do is change U to A, which requires only 1 operation, right? So that's why we have a 1 over here. And from SU to SAT, what do I do? Well, I know from SU to SA it requires only 1. So all I need to do is one more insert operation to get SU to SAT, right? So in other words, from SA to SAT, I can go by inserting one more operation, right? So we can go on like this. So let's do one more thing. This is tricky. So I want to reach SATU from SU. Okay, so I have SU and I have SATU. So how many, what would be the edit distance? So note that S and S are common, U and U are common. It's only the A and T which needs to be inserted in between. So 2 insert operations are sufficient here, and so you see 2 over here. But this looks really difficult, isn't it? For each and every case, you start thinking and computing the edit distance. And then you start filling this table. But let's say you somehow fill this table, then the last cell of the table, that's over here, will tell you what is the edit distance between Sunday and Saturday. That is how many changes, how many inserts, deletes, and replace that we need to do to arrive at Saturday given we have Sunday. Okay, so that's the point of doing this table. But can you see some pattern here? Can you somehow find some rules of filling this table so that we could mechanically in an algorithmic fashion complete this table. Take a pause and look at these rows and columns and think about the entries that are getting into this table and see if you can find some kind of recurrences. This is a good time to pause. You have observed this already. If not, well, it turns out uh, that we are simply doing for any square, we are simply adding 1 to their the other 3 squares, this one and this one, and taking the min of them. So we either take min of this plus 1, this plus 1, and so we calculate this plus 1 and this plus 1 are 2, but s to s when is 0, so that plus 1 is the minimum value that I would get, so I just take that plus 1. So that's what I'm trying to do. The only exception to this case is when I have the same characters on both sides. So if the characters are the same, I simply take down whatever is on the diagonally adjacent cell. Why is that so? Uh, when I have to change nothing, I mean, then whatever was the history, so that's all I need to remember. So whatever was before s, so whatever the edit distance took to reach here, that's all I need to remember, and I could just copy the same thing over here. Since the s is same, nothing changes, right? So I can just bring down the element diagonally here. So that's what this is giving us. D of any cell I comma j is simply min of either d of I minus 1 comma j. So in for now we assume that all operations take a weight of 1. So these are all weights of deletes, inserts, and replace. So if the problem gives different weights, you could always apply them here. But for now, if we assume that all these have weight of 1, so you could replace these with 1. So we take min of I minus 1 comma j plus 1. So I minus 1 comma j plus 1 would be horizontally adjacent element. I comma j minus 1 plus 1. So I comma j minus 1 would be vertically adjacent element, and I minus 1 and j minus 1 would be the diagonally adjacent element, right? So if we have these elements, so let's say we have I and j, so let's say I goes, so you could name any axis as I and any axis as j. So if let's say this is I comma j, and then we have I minus 1 comma j minus 1 diagonally before, and then let's say I minus 1 comma j, and then we have I comma j minus 1. So let's continue with this. So that's this part for d of I comma j, and after that is done, for the first column I comma 0, we know what to do. It's and also for 0 comma j, we simply keep incrementing by 1 or by the weight, right? So it's as simple as it is. So for this, the first column, we just keep incrementing. For the first row, we just keep incrementing. So that's what these two are about. And finally, d of 0 comma 0 is 0. This is just for completion. Okay, so that explains everything, explains the Levenshtein's algorithm at least. Here is a pseudocode for Levenshtein's algorithm, which simply implements the same idea that we have discussed and initializes the other cases here and here. So this must be pretty obvious. Please take time to read this for yourself. Okay, so now that we have Levenshtein's distance measure, a curious question here is, can we use this to answer wildcard queries? What do you think? Well, the answer is yes, you could probably use it, but note that this is very, very expensive. So if you have to convert, you have to compare edit distance with, you have to compare every query term with every dictionary term and compute the edit distance. It's going to be really expensive. So in such cases, we usually apply some heuristics to reduce the space of comparison, and then we go ahead and apply the index. Let's look at one more idea of some approximations that we could apply to reduce the number of terms that we want to compare. So one idea comes from the K-gram for spelling correction. So let's say we have an example here where I start with bold, which is misspelled as board, and I want to detect it, right? So if I take the bigrams in this case, the query board will get split into, let's say, BO and RD. Is not only going to match board in the dictionary term, which is good for me if it does match, but it also matches with boardroom, for instance, right? So it gives multiple candidates, and now we have to select those all those candidates and apply some other algorithm or directly compare them to get to a meaningful output. Now consider doing some more refinements on this. Can you do something to make this better? It turns out that computing Jaccard similarity over the k-grams is a slightly better idea. A Jaccard coefficient is simply A intersection B over A union B, where A and B are two sets. So let's say we compute bigrams of the words board and boardroom with the end markers on. Let's say if I put a dollar here and here, similarly a dollar at the beginning here and a dollar at the beginning here, then I would get all these bigrams for board and all these bigrams for boardroom. So okay, these are union of both. So if I take the bigrams here and the bigrams here and then union them, that's what I have in the denominator. And if I take the intersection, the common ones are here in the numerator. And if you take if you see what fraction of this is this, you get a measure 3 over 12, which tells you how much bigram similarity do we see in some words. And I can use this measure as a heuristic to filter out some terms in the dictionary and then only take those where I feel that there is a better match, and then apply heavier algorithms or just do a direct comparison if I need. Okay, so that was about isolated term corrections. But what if you want to do context-sensitive spelling correction? So we discussed the example of flu from Delhi, and if we were to try to correct this, flu 4 is probably another dictionary term, from is another dictionary term. So which term should we select? It's quite obvious from our experience that it should be from, but how did we know? How can we use this idea of how we know to improve the search engines? Well, the surrounding words are giving clues that this word usually does not appear in the query log. So one potential solution is to look at the query log frequency. A query log is just a huge log of all the queries that we have received so far. So we look at the query log frequency of phrases and detect that, all right, so if I just do a simple change to form to from, so I have another word with an edit distance of, so what is the edit distance from form to form? Right, it should be 2, isn't it? So we just replace O and R. So edit distance of 2. I get another word which is which appears a lot more number of times in my query log. So this should be the right phrase. So I could use log frequency to do this. We'll stop here for this session. In the next session, we'll focus on phonetic corrections. So thanks for watching this lecture, and hope to catch you with more in the next one. Thank you. Bye-bye.